Hello again. Let's continue our discussion of two-dimensional motion. In the previous video, our motion had no acceleration. And in this video, we're going to add acceleration. But before we do that, let's review what our equations looked like with no acceleration. So we had that the x component of the velocity was just a number, a constant. So I'll just put down number. And the same thing, a similar thing with the y component. The y component was just a number. Okay, and as far as the x position, it was something like this. We had x equals the beginning position plus v sub x times t, and y was the beginning y position plus v sub y times t. All right, now if we have acceleration, then our x velocity is going to look like this. It's going to be the v sub x is going to be the beginning, the initial x component of the velocity, which I call v sub 0x. And there's the acceleration times time. And this acceleration times time is pretty simple, but in order for it to be that simple, we need to make the assumption that the acceleration is constant. And for the most part in this class, we're making that assumption because things are already pretty complicated. So we don't want them even more complicated. We have a very similar looking thing for the y component of the velocity, initial y velocity plus the y part of the acceleration, the y component of the acceleration times time. And for the x and y positions, we have that it's the initial x position plus the initial x component of the velocity times time plus 1/2 at squared. And the a is the x component of the acceleration. It is the same as this acceleration here. And then a similar thing for the y position. It's the initial y plus the initial y velocity times time plus 1/2 at squared, where a is the y component of the acceleration. And in terms of the big five equations that we've sort of standardized on in this class, if you want to look at the notes on page 2-18, chapter 2, page 18 of the notes, where this would be big five equation number 3. Okay. Now, this formula here is going to take care of most of our homework problems and so on, but there are cases where the other big five equations are helpful, and the one that the book really likes, and there are going to be problems that entail using this, is this one here. It's I guess it's formula number 5, big five number 5, and so you'll recognize these formulas. It's just that now we have an x component and a y component to it. And so let's see if we can read this. So the x component of the velocity squared is equal to the beginning x component of the velocity squared plus 2 times the a component of the acceleration times delta x, so the change in position. And remember, this would be x minus x0, right? So you might maybe you're more used to it this way. And so that's delta x. And then you've got something super similar to that for the y position. Okay. We're now ready to start talking about projectile motion. So a projectile is something flying through the air or flying through space. But the thing is, it's being pulled by gravity. So a pretty good example of a projectile would be you're throwing a rock, and the rock flies through the air. And when you drop a rock, it's falling straight down. But free fall, which is this term I'm using right here, an object in free fall, doesn't mean something that's necessarily falling straight down. You could have thrown it straight up. And as soon as it leaves your hand, it may be moving upward, but it's being pulled down by gravity. We say, okay, it's in free fall because gravity is really the only thing that's affecting it. It's the downward pull. We're ignoring air resistance in all of this. Now, if you take a rock or a baseball or a football or whatever and you throw it, it'll make this nice curve across. And that too is in free fall because as soon as it leaves your hand, the only force acting on it is gravity. Okay, so let's talk about the x and y pieces of the motion of something that you're throwing. So x is going to be the horizontal part of the motion, and y is going to be the vertical part of the motion. Now, gravity pulls down. Gravity doesn't pull sideways. So that means that the x component of the velocity is not going to be changing. So we can write that v sub x is the same, and it's always the same as whatever the beginning v sub x was. On the other hand, we have an acceleration. It's minus g, the minus meaning that it's downward, and g is 9.8 meters per second squared. Although occasionally we'll make our arithmetic easier and approximate 9.8 by 10. But anyhow, okay, so we have the y component of the velocity is equal to the beginning y component of the velocity minus gravity times time. All right, now from this we get this. So the x position is going to be the beginning x position plus the x component of the velocity, which doesn't change, times time. And let's see, maybe use a different color for the y position. This formula becomes this. So we have that this process here is because of the big five. So we have y equals the beginning y position plus the beginning y velocity times time, plus 1/2 the acceleration times time squared, but the acceleration is minus g, right? So we have a equals negative g, and the convention is to move the negative sign out from here and put it here. So that's why the negative sign is there. Minus 1/2 gt squared. And I mentioned to you that the book likes to use these formulas here. And so sure enough, here is what happens. In terms of the x component, it's pretty boring. It's just v sub x squared equals the beginning v sub x squared. I mean, there's no surprise there, but but then over here they're using this formula, and it's getting used. Let's go down. It's getting used. Let's keep my arrow going down here. Okay, so now we have the y position, the y velocity squared equals the beginning y velocity squared minus twice gravity times delta y. And here the delta y is the y position minus the beginning y position, like that. Okay, so that's what that is. Okay, so now we have just barely set up projectile motion and the math that it involves. And there's a lot more stuff to talk about. And so let's see. What I think I'll do is talk about some of the essential facts of free fall. So the first fact is that we've separated the up and down motion from the left and right motion. So the sideways motion has no effect on the up and down motion. So a ball or a rock or something that you throw sideways, it will fall just as quickly as a rock that you just drop, from without any sideways motion, a rock that falls straight down. So I'll say that again. You throw a rock sideways, it'll hit the ground just as quickly as the same rock just dropped. And after this video, in my playlist, there's some videos that come after that illustrate that. The next thing is that the motion, the XY motion of the rock is a parabola. And you're used to parabolas that look this way. This would be a parabola. And to make a parabola like this, you have this is maybe y equals x squared. Well, so as you go to the right, move and so your x position is increasing, linearly increasing as you go to the right. Your y position, which depends on the square of where you are, it does this. It's a parabola. Now, the parabola that we're going to be looking at is going to be something like this, right? So it's still a parabola. It's upside down, but the thing is that the reason why this is happening is because the y position entails a negative gt squared term, and so x is going to be increasing linearly with time, whereas y is going to have this term in it, and so you're going to wind up with an upside down parabola. So mathematically, I'm saying here x increases linearly with time, whereas y is a quadratic function of time. Yeah, and so for example, if you were to graph this, you would get an upside down parabola. X equals 10t, and then this thing here. You get this upside down parabola. Okay, let's take a look at some common questions, typical homework problems, typical exam problems, and they'll illustrate a lot of the ideas in projectile motion. A rock is thrown sideways from a cliff with an x component of velocity equal to 4 meters per second. The cliff's height is 30 meters, and we'll call it h. H is 30 meters. how long will it take for the rock to land below? So how long is it going to take for it to go from a height of 30 meters down to a height of 0 meters? And at the same time, how far has it gone in the x direction? So the answer to B is called the impact position. In this problem, I'm calling it x impact. And it will hit the ground at T impact, the impact time. And the impact time is basically what question A is asking. Okay, so now the initial y velocity is 0, right? Because it was thrown horizontally. And how far it falls is given by 1/2 gt squared. I'm not, at this point, I'm not really paying attention to the negative signs. We'll have to take care of negative signs later, but right now this is a simple enough question that it's not necessary. So we have that it falls this distance, h, and how far you go with an acceleration is given by 1/2 at squared, and our acceleration is g, and so we've got h equals 1/2 gt squared. If I take this, if I isolate the t squared and then take the square root of both sides, I get t equals the square root of 2 times the height over g. I can now plug in my numbers. I was given that the height is 30 meters, and we're going to use g equals 9.8, and I plug in my numbers, and I get 2.47 seconds. So that is my t impact. So we have taken care of the A part of the question. How far has it gone? Well, we know the x part of the velocity that was given. It was 4 meters per second, and it's not changing, right? There's no acceleration in the x direction. And so now that we know the impact time, we can use position equals velocity times time, or distance is velocity times time. And we're talking about the impact position, so we'll call that x impact. It's equal to the x part of the velocity times the time of impact. You plug in the numbers, right? The 2.47 seconds came from there. This was given, the 4 meters per second was given, and you get the answer, 9.9 meters. So it moved 9.9 meters in the x direction before hitting the ground. So we just did a problem which was extra easy because the initial velocity was just horizontal. There was no initial y velocity. In this next one, there is a y velocity at the start. And so it's going to be quite a bit more complicated because of that. Let's take a look. So it's the same as the previous question, but now the rock is thrown up and to the right. And the y component of the velocity is 7 meters per second. So our questions are the same as before. How long does it take to hit the ground? And how far will it have gone when it hits the ground? How far in the x direction will it have gone? So here's my cliff, and here is my initial velocity, my v0. And the x component is the same as before. It's still moving 4 meters per second in the x direction, but simultaneously the y component is 7 meters per second in the y direction. So these are the initial velocities. All right. Now, because we have up and down motion, we have to be careful with the negative signs. And so we're going to go with the convention, up is positive, down is negative. And all right, so here are our initial information. V0y is plus 7 meters per second. Our initial y position is equal to the height of the cliff, which is 30 meters. And y is 0 meters when it hits the ground. So this is the end of the experiment. We get y equals 0 meters when t equals t impact. So if we go back to the formula that we had gotten before, let's just scroll back and find it. Okay, it was sort of this formula. I think I went a little too far. Let's go back to here. Okay, this is the one I'm looking for. Okay, so this formula here is for projectiles. So let's go ahead and copy it down to where we need it, and that is right here. Okay, this is where we need the formula. Now, notice we know what y is. It's 0 at impact, right? So this is impact. We know what the initial y was. We were at the top of the cliff, so that's the 30 meters. We know what the initial y component of the velocity is, right? It's a given, 7 meters per second. And we know what is g, it's 9.8. The thing that we don't know is the impact time. But we have this formula here, this equation, and we can solve for t. It's going to get ugly because it's a quadratic equation, and we need to rearrange this thing so we can use the quadratic formula that you learned in high school, I think. And so in order to make this thing work out, we have to massage this thing so that it looks like the standard quadratic formula that we're used to from high school. And so AT squared plus BT plus C equals 0. If we make it in this form, then we can use the quadratic formula. So what I'm going to do is negate everything and add y to both sides. So if I negate everything, I'm going to have negative y equals negative y0 minus v0 yt plus 1/2 gt squared. And then I'm going to add y to both sides. And so I have negative y0 plus y. And I have, instead of v0 yt, I have negative v0 yt. And instead of negative 1/2 gt squared, I have positive 1/2 gt squared. So if I do this step carefully, this is what I get. Now the other thing that I've done is I've kind of moved things around, right? So instead of having the gt squared at the end, I want it to look like my quadratic formula. So I kind of moved it over here to the left. I left the v0 yt term in the middle, right? Because this t term is in the middle. And then y minus y0, those are constants. We want the constant to be at the end here. So I've done all of these little steps to make it look like the setup we need to use the quadratic equation. All right, Now, here's the actual quadratic, you can look this up in your old algebra books, or these days, Wikipedia is pretty good. So it's minus b plus or minus the square root of b squared minus 4ac, all of that over to a. I have a feeling that's probably coming back to you. You're probably hoping you'd never have to use this formula again in your life, but sorry, here it is. It's going to bug you again. So we want to identify what is the A, what is the B, and what is the C for use in the quadratic formula. So the A is this piece here. Whoop. Is this piece here, the 1/2 G. The B is the minus V0y. That's the B. And the C is this stuff here, y minus y0. So that's what I'm writing here. Here, you see, this is the A part right here. G is 9.8, is half of that. Here is the B part, minus 7. And y is 0, and y0 is 30, so here is the C part. So it works out that A is 4.9, B is negative 7, and C is negative 30. And so now we carefully plug in our numbers into the quadratic formula. So minus B becomes minus negative 7. And plus or minus the square root of negative 7 squared. Of course, the negative doesn't matter here because you're getting squared. Minus 4ac, so 4. Here is the A, the 4.9. Here is the C, negative 30. So we have a negative and a negative, right? That's going to come out positive. And we carefully, work our way step by step, plugging it into our calculator. Don't forget that there are two answers, a plus and a minus answer, which is confusing, I know. Only one of those two answers is of any use. And so part of your task as physicists is to figure out what piece of the answer is useful and which piece is garbage. So you can't have a negative impact time, so that's garbage. You throw it away. And so this is our answer, 3.29 seconds. So it takes 3.29 seconds for it to hit the ground. Yay, we got it. T impact is equal to 3.29 seconds. Whew. Now we want to get X impact, how far it went. Now that's going to be pretty easy actually because it's moving in the X direction at a constant rate. So here is our formula. It's the X component of the velocity times the T impact that we just figured out. And we were given that X, the Vx is 4 meters per second. And we just figured out that the impact time is 3.29, and you get your answer, 13.6 meters. Now, an important thing to notice, maybe this is obvious, but I'll point it out anyway, is that it went further. It went 13 meters. It went further than when you just throw the rock sideways. 9.9 is what you got when you just throw the rock sideways. So you probably know this intuitively, but if you want to get distance when you're throwing something off of a tall place, you're going to get more distance if you give it a bit of an upward slant when you throw. Okay, so I'm going to stop here. And now what I want you to watch is the Hewitt demonstration where he makes two things go and they both fall at the same time. Two marbles fall at the same time, but one falls straight down and one falls sideways. I want you to watch that. It's the next thing in the playlist. And then, just for fun, there's the falling monkey demo, and I made those videos a long time ago.